The final topic that we're going to deal with in Trig Part 2 is this idea of angles of elevation and depression. Alright, now really the key thing to remember in angles of elevation and depression is that they're always measured with the horizontal. So in other words, an angle of elevation or depression is going to be an angle from one point either up to another point or down to another point. But again, the key is that they're always going to be measured with the horizontal, right? So this angle right here would be an angle of, right, it was up, so it's an angle of elevation. And then this angle here, when we go down, would be known as an angle of depression, right? And even though you might say, well, that's a clockwise angle, so it's going to be negative, we're not dealing with any negative angles here, right? We're thinking this more along the lines of geometry rather than trigonometry, so we're really just dealing with positive angles here. So even though the angle of depression rotates clockwise, we're still going to consider it to be a positive angle. Right? So again, really the most important thing to remember here is that these angles, angle of elevation and depression, are always measured with the horizontal. Right? If you remember that, you're probably in pretty good shape, because the mistake that people make is a lot of times they measure them against the vertical axis instead of the horizontal axis, and then it throws off the whole problem and you can't get the right answer that way. Right? So they're always measured with the horizontal is a key. Okay, so first things first. First question here. The angle of elevation from a man 6 feet tall to the top of a nearby hill is 65 degrees. If the top of the hill is 400 horizontal feet away from the man, how tall is the hill? All right. So what's the scenario? You've got this guy here, this man, 6 feet tall, and he's looking up, right, because it's an angle of elevation, so he's going up to the top of a hill at an angle of 65 degrees. So what you've got here is, you've got this, again, it's horizontal, it's measured against the horizontal, and he's looking up at this hill, and let's say here's the hill. And you've got, there, looks like a big rock, but we'll consider it a hill, right? So this angle of elevation in here, right, this angle here, this is going to be 65 degrees, okay? And the top of the hill, right, which is right here, is 400 horizontal feet away from the man. So what that tells us is, again, you can see what you're doing here is you're forming a right triangle, right? That's what we've been dealing with here is right triangles. So you form a right triangle like this with a horizontal distance. So in other words, this horizontal line here would be 400 feet. And they want the height of the hill, right? So they don't want the distance from the man to the top of the hill. They actually want the height of the hill. So they want this here. So this is like your unknown, and I guess I can call this B, right? Because I have A, which is 400 feet. If I want to call that A, and then the height of the hill B, and then the hypotenuse there C. So I'm trying to find B. And again, this is just like what we did with solving the right triangles. What you've got to do is you've got to consider what you're given and what you're trying to find. So in this case, I'm given this angle here, right? I'm given this side here, which is the adjacent side, okay? And I'm trying to find this side here, which would be the opposite side, right? So I've got the angle, the adjacent, and the opposite, which means I'm going to use tangent. Right? So what do I know? Again, the definition of tangent is that the tangent of the angle, which in this case is 65 degrees, is going to be equal to the leg opposite, which is B, over the leg adjacent, which is 400. And that little shortcut that I had given in one of those previous videos said that if the unknown is in the numerator in these problems, you're going to be multiplying, right? So you're going to have B is going to equal the 400 times the tangent of 65 degrees. And again, that's the exact answer, but in this case, we want a practical answer here. So we want to turn this into our degree mode again. And we want to go back and then do 400 tan 65, and we'll get 857.8. So 857.8 feet. And this is just a minor little technicality here, but it is something that you should keep in mind. Is that actually the height of the hill? Not quite, because it was the angle of elevation from the man to the top of the nearby hill, and his eyes are basically, you know, almost at the top of his body, right? So really, B is not quite the complete height of the hill. You really also have this little area down here, which is an extra, essentially 6 feet, because he's a 6 feet tall man. So technically, I guess, the height of the hill is really 857.8 plus the 6 or so feet of his eye level, right? So it's really 863.8 feet, right? So that's probably a more accurate estimate for the height of the hill, 863.8. Okay. But we also have the other kind of problem, right, which was angle of depression problem. So this is where you have a point, and in this case the point is not a man, it's actually a plane. So if we have this plane, I guess that's okay, right? The angle of depression from the plane to the runway is 21 degrees. So let's say the runway is down here, and I guess they want the front of the runway, right? You'd say the front of the runway, which is this point here. This is the runway. And the angle of depression from the plane to the runway would be 21 degrees. And again, this is where people make the mistake a lot of times. What they do is they draw in this vertical line here, but you don't want that. Remember, what we said was the angles of elevation and depression are always drawn with the horizontal. So this, there, that angle, right, measured against the horizontal down to the runway is your 21 degree angle. And the plane is flying at an altitude of 22,000 feet. So this leg right here, that's your 22,000 feet. And then they want the straight line distance, right? How far straight line distance is the plane from the runway? So what they're really asking you for is this value right there, C we'll call it, right? So again, you ask yourself what's involved. In this case, I have an angle. I have this leg, which is the leg opposite, and I have the hypotenuse. So which trig function involves the opposite and the hypotenuse? That would be the sine, right? Remember SOHCAHTOA? So again, definition would be sine of 21 degrees equals, sine is the opposite over the hypotenuse, which is 22,000 divided by the hypotenuse I'm trying to find, which is C. Now here the difference is my unknown is in the denominator. So again, the shortcut was, we said, when the unknown is in the denominator, you're going to be dividing the value that you have, 22,000, by the trig function, which is the sine of 21 degrees. So in this case, it's 22,000 divided by the sine of 21. And I'm already in degree mode, so I can just do 22,000 divided by the sine of 21 degrees. And I would get 61,389 feet. So the straight line distance from the plane to the runway in this case would be 61,389 feet, which is about 12 miles, I guess, right? Because you figure roughly 5,000 feet in a mile, so 12 times 5,000 would be 60,000. So it's about 12 miles away from the runway. Okay, so that would be an angle of depression example. And really, I mean, it's pretty simple once you set up the picture, but the key is setting up the picture accurately. And to set up the picture accurately, you got to remember that the angles of elevation and depression are always measured with the horizontal, not the vertical. Right? They're always measured with the horizontal. So remember that.